Okay, rather than doing this Geometry Sketchpad investigation right here, we're going to hop over to, there's an applet posted in your Google Doc. But here's what we have in this picture, this GeoGebra applet, is a circle, and you've got two tangent lines, two lines that are touching the circle, and then they come out here to point E, and they meet out here at point E. And what they ask you to do is to slide this slider. Okay, and so when you slide the slider, it pulls out two radii. Now notice the tick marks on the two radii because radii are congruent no matter where they are in the circle. The next part shows that the radii are both perpendicular to their respective tangents to these two tangent lines, which was our last theorem. But then they draw out another line going from the center of the circle out to point E. And what you might notice is that that creates two triangles. Now specifically, these two triangles are congruent. I want you to think about for a second which one of our 5 triangle congruency postulates would allow for these two triangles to be congruent. We have the hypotenuse is congruent because it's a common side. You have the radii are congruent, and you have the right angles. So this would be what? Hypotenuse leg that says these two triangles are congruent. So the next theorem says because those two triangles are congruent, then by CP/CTC, these two pink lines are congruent. So going back to theorem 10.11, it says if two segments from the same exterior point are tangent to the circle, then they are congruent. So here are those two pink lines that were on our GeoGebra applet. And the idea being that they are congruent. Now, I like to call this theorem the elf-hat theorem. Because if you draw a little elf, you got to draw the pointy ears, right? Then the two sides of the elf hat are always congruent. It's just an easy way to think of those two tangent lines coming to the same exterior point as always being congruent. So I'm going to call this the elf hat theorem, just a silly way to remember it. All right, so here we go in example 4. Find x, assume that the segments that appear to be tangent really are tangent, and then find the perimeter of the triangle. So I hope what you're thinking about right now is that here is my elf, and here are his pointy ears, and that the two sides of the elf hat are always congruent. So when I want to solve for x, I'm setting 4x plus 2 equals 2x plus 8. So to solve this equation, I'm going to subtract 2x from both sides. So 2x plus 2 equals 8. Subtract 2 from both sides, so 2x equals 6. Divide by 2, I'm running out of room, and x equals 3. But wait, there's more. Once I've found x, then I'm supposed to find the perimeter of the triangle. So here's my triangle. And so if I want to find the distance all the way around, 4 times 3, I'm just replacing x with 3. This is 12. 2 times 3 is 6. 6 plus 8, this will be 14. Because this side is also the same, it'll also be 14. So my perimeter is 14 plus 12. So that's 28, 30, 40 would be my total perimeter. 40 units. So tagging on to that, the next piece is still talking about tangent lines. It's just talking about going back and redefining some of these things that we did previously, but now you know the correct terminology for it. So inscribed in the circle means triangle is inscribed in if all the vertices of the triangle lie on the circle. In other words, these sides of the triangle are all chords, right? Now you know the correct word for that. A triangle is circumscribed about the circle if each side of the triangle is tangent to the circle. So earlier when we studied circumscribed polygons, you didn't know that the word for this, when each one of these sides of the triangle touches the circle, is that it's tangent. So hint, whatever's on the inside is inscribed, whatever's on the outside is circumscribed, and this is true for all polygon circle relationships.